Hi, I'm Ben-Yaakov. This presentation is entitled Intuitive Explanation of Coupled Inductors Sepic Converter in comparison to the Flyback topology. I'd like to acknowledge that this video was inspired by an exchange with Isaac Cohen of TI. We are familiar with the Flyback converter. Here I'm showing a basic configuration. We have a transistor. This is a coupled inductor. And then when the transistor is on, we have the current going up in the primary inductor. And then when the transistor is off, current is coming off the secondary and then dropping down. I'm showing it for the CCM. Of course, the DCM also is possible. Now the Sepic, this is the single-ended primary inductor converter, as it's called, Sepic, was actually invented at IBM many years ago. And there are actually two versions. One is the uncoupled, in which you have two inductors. This is a transistor, two inductors, a capacitor, and then there is a rectifier. And then there is a version of a coupled inductors. Again, we have this capacitor and then the rectifier. I'm showing here another way of drawing the same thing because sometimes you can see it in this way or that way. Of course, these are the same circuit, just drawn differently. Now, one thing is clear because we have this capacitor here. We cannot have separate ground, so it's not an isolated configuration of topology. You have to have the same ground at the input and at the output. So this is one point that has to be emphasized at the very beginning. And now I'm going to show something which I think is kind of new, at least to me, because I've just thought about it. And that is that the Flyback and the Sepic are basically the same topology, generic configuration, and they work the same in the basic principles, although there are some differences which I'll talk about, and there are some benefits to the Sepic, and that the transfer ratio in the case of the Sepic is exactly like in the Flyback, okay? Like it's V out over V in, it's D on over D off. Now I'm going to demonstrate it by considering the ideal Sepic and Flyback, you might say, and therefore we are talking about transfer ratio of the windings of 1 and coupling coefficient of 1. I'm assuming that the capacitor of the Sepic is very large, okay? So the actual Sepic will behave a little bit later. We'll see it later on in the simulation. I'm starting this explanation by considering the situation that the transistor is on. The transistor is on, so there is a short here. And as you can see, we have this path here. So the capacitor is connected to this secondary inductor. Now the voltage across the primary at this stage is V in because there is a 0 here and there is V in here. And due to the dot location, there is a negative voltage here. So the capacitor is charged or will be charged eventually to this polarity when the value of the voltage is V in, okay? This is the voltage of the capacitor. Now I'm considering the situation in which the transistor is off. At this stage, of course, the current is coming off the secondary to the output, but I'm now looking at this loop here of voltages, okay? This loop here. So we start with V in, and then we have a drop of this primary inductor. Now the voltage here is a reflection of the voltage here, which is clamped to the output. So the voltage here is V out. Now we're going here in the same direction. So this is V in plus V out. Now the capacitor is assumed to be charged to V in as we have seen earlier. And then of course we have this voltage here, V out, which is we go in the negative direction. So this is the summing up, and as you can see, it sums up to be 0. What does it mean? It means that the capacitor doesn't have to change at all between on and off. So it really has no current through it. This is for the ideal case, of course, I'm talking. And therefore, the behavior of the Sepic will be exactly the same thing as the Flyback. So there is no change in the operation whatsoever between the Flyback and the Sepic in this respect. Now, as it turns out, a coupling coefficient of 1 is not good for the Sepic. And the reason is that looking again at the situation when the transistor is off, we have here a path here, which is like a resonance circuit. And this resonance circuit will cause oscillation and maybe instability. So in fact, the Sepic converter works best with some leakage, that is with the coupling coefficient which is smaller than 1, which is unlike the Flyback converter. Now when we have leakages, then these actually tend to suppress the oscillation because the quality factor now becomes lower, in fact, because the inductances are small, and therefore it's a better operating point. And there is a very important point here, is that the contrary to Flyback, the leakage energy is recycled in the Sepic. That is, you are not suffering from what is happening with the Flyback, in which the energy in the leakage is actually lost unless you are using things like active clamp or some other approaches. But the basic Flyback suffers from leakage, and leakage reduces the efficiency of the Flyback. Here, it turns out that not only that it stabilizes the operation, but actually it's good for the operation of the Sepic, as we'll see it later on in the simulation. And here is the simulation that I've set up. This is the Sepic. I've put here a very large capacitor, okay? This is the switcher. Here we have the rectifier. I've also added here a circuit for calculating the RMS of the primary inductor here. And then we have a Flyback, which is very similar, except that there is no capacitor, of course. I've used the same ground, doesn't matter. And I'm comparing now the two for the ideal case in which the coupling coefficient is 1. I've made this capacitor fairly large, which is not realistic. I'll talk about it a little bit later on, what happens when the capacitor is smaller. So this is a comparison between these two converters for ideal coupling. And lo and behold, here we have this gate, which is the same for the two. And you see here, this is the diode current, the output diode current, this diode and this diode, and they are exactly the same. Okay, no matter this capacitor which we have in this Sepic. Now, the current of the primary inductor in the Flyback is this square waveform, which is the typical one. Here we see it a little bit smoother. And the reason is that the capacitor is not infinitely large, and therefore it is charging and discharging to some extent, but this does not affect the operation of the circuit. Okay? Still, the transfer ratio is exactly the same as in the case of the Flyback. Now, once I reduce the coupling coefficient, then in Flyback, obviously, I'm starting to get some oscillation and spikes and overshoots, etc. We don't see it in the Sepic. Everything is smooth and nice. You see the current of the output diode, very smooth. We see also the primary inductor current, very smooth, no oscillation, nothing. So you see that there is a big benefit in this Sepic in that it is not switching the leakage on and off with the open circuit, but rather it's locked within the loop. So to reduce the oscillation in the Flyback, I've done here what is usually done in actual circuit. First of all, I've added here a clamp so that the voltage will not shoot up too high, and then some snubbers here and here to lower the oscillation. Otherwise, it's the same, except that now I've actually reduced the capacitor to something more practical, like 10 microfarad. The coupling coefficient is 0.99, which is kind of reasonable, like 1% leakage. And so this is now a more realistic comparison between the two. So here it is. The Sepic is again very smooth, very nice. This is the drain of the Sepic. This is the drain of the Flyback after I've added this snubbers and clamp here. You see the operation of the clamp. Now the current output of the Flyback here is lower because of the losses, and also the output is much lower. It's 20 volts rather than 24 because of all these losses of the snubber and the overshoot, etc., etc. So there is no question about that when it comes to the effect of leakage and recycling the energy, the Sepic has a lot to offer. And here are some more waveforms. What I'm showing here is the primary inductor current in the two cases. Well, the square one is the Flyback, of course, and this smooth one is the Sepic. And here is the current of the secondary inductor, the output. Again, the current is very typical here in the Flyback, while here we see it very smoothed. And this is again because of the fact that we have the leakage, which is sort of smoothing the operation and sort of averaging it out. And then again, we see the output current through the diodes, although the oscillation is lower, but still there are some oscillation, of course, because it's very difficult to suppress everything. And the more you add suppression, the higher will be the losses. And this is the RMS of the primary. And the Sepic this one is lower, of course, because you can see it here. This is now the current of the Flyback, and this is the Sepic, and obviously the RMS of the Flyback is larger. So comparing the two, we can say the following. As far as the gain goes, the gain is the same. The transfer function is the same, except that in the Flyback we have a way of changing the ratio quite a bit. Like if you like to have a step down, a heavy step down or step up, you don't have just to change the duty cycle. You can do it by the turns ratio. You cannot do it with a Sepic. So Sepic is good when you need a gain of, say, 1, and then with a gain higher than 1 and lower than 1. Like if you have a battery and like to feed the load, which is sort of like the voltage of the battery, and then the battery is higher than what is needed and then lower than it's needed, and you can accommodate this change here. So this is one big difference between the two. Obviously, Flyback has isolation, which you cannot get with the Sepic, but all the other things are actually better in the Sepic. You don't need a snubber, you don't need a clamp. Well, in some cases you'd like to add some snubber, but in general, the requirement is really very mild. And then EMI, of course, in the Flyback is much higher than in the Sepic, and the RMS current of the primary and secondary wires, of course, will be lower. So we see that the Sepic has a lot to offer. I know that some people are sort of avoiding the Sepic as being sort of complex and somewhat mysterious. Well, it is not. It's very similar to the Flyback, and with proper design, the bill of material is very compatible. So when you need this type of a gain, then the Sepic is a very good approach. So this brings me to the end of this presentation. I thank you very much for your attention. I hope you found it of interest, and perhaps it will be useful to you in the future. Thank you very much.